So let me share my screen. Yes, the screen is visible. Hello.
Yes, sir.
Okay. So let's start our class. So in our last class, we completed up to here actually. So before we did what is infinite bus, we actually found out the very important relationship, that is P and our Q, or P and delta is strongly coupled, and Q and V have strong coupling. Okay, we did find out this one. Okay, someone's mic is on. Please mute yourself. Please mute yourself. Someone's mic is on. Okay, so we talked about P and delta have a strong coupling and Q and V have a strong coupling, where we said that this delta is also known as our load angle or our torque angle. Okay, also known as our power angle. Now, whenever we are talking about this power system performance, specifically in our part, since we're talking about synchronous generators and all, we have to know certain things about our synchronous machines. Okay, so we'll be starting with the synchronous machines. So before we uh, do that, we can also see that how we actually denote a synchronous generator. As you can see, the synchronous generator is connected to an infinite bus. And what is an infinite bus? It is a bus which is having constant voltage, constant frequency, infinite inertia, and zero internal impedance. Why it is so? Why it is so called? We have discussed those things in our last class. Okay, so in our class, we were talking about, in this class specifically, we were talking about the synchronous machines. Okay, and specifically, please note, since we are talking about the synchronous generators, we'll be confining ourselves only to the power system aspect of the synchronous machines. Okay, only to the power system aspect. We are not going to the details of the design and so on. Only those parts which is needed for our understanding for our power system will be concerning ourselves which only about those aspects only. Okay, so when you're talking about synchronous machines, these are the most important element of a power system. Okay, so it is an AC rotating machine whose speed under steady state condition is proportional to the frequency of the current in its armature. Okay, synchronous machine is an AC rotating machine. As you know, it converts the mechanical energy to the electric energy, and it feeds to the power network in case of a generator, and it draws electrical power from the network and converts it into mechanical form in the case of a motor. Okay, so the here what happens, that the machine acceleration is controllable, which determines the flow of watts, that is volt ampere reactive, into or output of the system, into or out of the machine actually. And in a synchronous generator, we use DC current, which is applied to the rotor winding, which is also known as the field winding, which is producing the rotor magnetic field. Okay, so in the synchronous generator, the field winding on the rotor is energized from a controllable DC source, and the rotor is driven by what? The rotor is driven by external means producing a rotating magnetic field. These external means can be the prime mover, can be steam turbine in case of our thermal power stations, and in case of our hydraulic power stations, they can be our hydraulic water turbines. Okay, so the prime mover may change, but whatever be the case, the stator winding is producing the three-phase voltage, that is around 11 kV. Okay, and at around 50 hertz. So the field windings in a synchronous generator are the windings producing the main magnetic field, that is the rotor windings for the synchronous machines, and the armature windings are the windings where the main voltage is being induced. Okay, so the stator windings uh, are the armature windings for the synchronous machines. Now, synchronous generators are actually of two types. There is another type of generator which is known as our induction generator also. These induction generators are actually used for our wind power plants. Okay, so all generators in any power system are basically synchronous type. So there are two types of synchronous generators: cylindrical rotor type, that is, what is the characteristics of a cylindrical rotor type synchronous generator? It is having small diameter, long rotor, small number of poles, and it is a very high speed type synchronous generator. And since because of its small diameter and high speed, this is used in our thermal power stations. And the other type is known as our salient pole type, or salient pole synchronous generators. Okay, others known as our salient pole synchronous generators. So salient pole synchronous uh, generators, what are their characteristics? They have projected poles. How projected poles? If you recollect something like this, okay, projected poles. Okay, these are the projected poles of a cylinder 4 rotor synchronous generators, and here it would be something like this and so on. Okay, like this. These are the poles for a cylindrical rotor, and these are the poles for a cylinder 4 rotor synchronous generator. Okay, the figure is not up to scale. You can just understand it. Okay, and there is means the gap, the air gap is not uniform between the stator and the rotor. If this is the stator and the rotor, in the stator rotor for a cylinder pole machine, whereas the air gap is uniform for a cylindrical rotor machine. Air gap means the air gap between the stator and the rotor. Okay, I hope you are getting my point. Okay, so what we are seeing that in cylinder pole type machines, we have projected poles as shown in the figure. Then we have unequal air gap. Okay, as I was saying, unequal air gap between the stator and the rotor. Then we have a large diameter. We have some figures also. We will see those. We have a short rotor and low speed compared to our thermal power stations, and that's why, because they are low speed machines, these cylinder pole synchronous generators are used in our hydroelectric power plants. Okay, so this is a typical picture of hydroelectric generator. You can see as I was saying, that they are having large diameter. So the diameter is very huge. As you can see, the size of the cylinder pole type is hydroelectric generator. Here it is written below. Okay, stator of a hydroelectric generator. Okay, similarly, this is the yes.
So what is the diameter?
Diameter. This is the diameter. Okay, huge diameters. Okay, that exactly value I do not know. Okay, I've just got the figure from this Brown Boveri Corporation. Okay, exact value ta amar mone nei. Okay, so it's comparatively very large compared to our cylindrical rotor synchronous generator. Okay, so this is the rotor for a cylinder pole alternator. As you can see, you have projected poles, large diameter, short rotor. Okay, whereas for a cylindrical rotor synchronous generator, here as you can see, the rotor of a non-cylinder pole alternator, that is a cylindrical rotor type. So here again, we have a long rotor, but the diameter is pretty small compared to the previous cases. Okay, so this is the typical figure of a cylindrical rotor synchronous generator, as you can see here, and this is the cylinder pole rotor type synchronous generator. Okay, on your left hand side, the figure, this is the cylindrical rotor synchronous generator. This is a cylinder pole rotor synchronous generator. As you can see, the air gap is uniform for a cylindrical rotor synchronous generator, and in a cylinder pole rotor synchronous generator, the air gap is unequal. Okay, the air gap is unequal. Okay, and similarly here, this is the stator, this is the rotor, and these are the field windings, as you can see, and this field winding, also known as our rotor windings, is excited by a controllable DC excitation source. Okay, separate excitation source lage seta alada kore dewa ache. Okay, so what we have now, so the cylindrical rotor alternator, as shown in the figure here, has a two-pole structure. This is having a two-pole structure. Okay, so the rotor is excited from a controllable DC excitation source, and the rotor contains P belts of slots. P belts of slots যখন আমরা বলছি, okay, when I'm saying P belts of slots, so this is again a typical figure where we have, which is only shown for our phase A. Okay, so this is the armature winding and the rotor winding, which is shown only for phase A. So as you can see, we have P belts of slots. Okay, so this is the phase belt for our A phase winding. Similarly, will be having for B phase. Similarly for C phase. Okay, then in this P belts, the field winding are placed. Okay, the rotor contains P belts of slots in which are placed the field winding conductor. So in these areas, okay, in these areas of the rotor, the field windings are placed. Okay, the field windings are placed here. So the rotor field conductors belong to the same belt, carry currents in the same direction. while the current direction alternates in the P belts. Okay, means যে কোনো একটা বেল্টে কারেন্ট ডিরেকশন কিন্তু সেম ডিরেকশন হবে, সেটা কিন্তু চেঞ্জ হতে থাকবে alternate ওয়েতে। ওকে, it will continue to change. So what will happen that the resulting rotor MMF will thus alternate around the periphery. Okay, in effect forming P magnetic rotor poles. The resulting rotor MMF will thus alternate around the periphery, in effect forming P magnetic rotor poles. So for the two pole case, what will happen? For the two pole case, the resulting magnetic flux paths are shown dashed, as you can see here. So this is the rotor MMF which will be produced. Okay, so this is the magnetic flux path, as you can see from the figure here. The figure that I have taken, this is available in your Elgard book. Okay, Electric Energy Systems Theory Elgard book. From there I have got this figure. Okay,
স্যার বেল্ট মানে কি বলছে
phase
এখানে?
ফেস বেল্ট বলছে যে এই যে ওটা কোনো পি বেল্টস অফ স্লটস, মানে কতগুলো পোল থাকবে, পোলের উপর ডিপেন্ড করে অনেকগুলো তোমার মানে স্লটস থাকবে। এই যে স্লটস গুলো বলা হচ্ছে না, এই যে দিস পোর্শনস, ওকে, এক একটা ফেজের জন্য এক একটা ফেজ বেল্ট থাকছে, এই যে, ঠিক আছে, এক একটা ফেজ বেল্ট থাকছে। ওকে, তাহলে তাহলে ফেজ এর জন্য 60 ডিগ্রি আছে, ফেজ বি এর জন্য আবার 60 ডিগ্রি করে, তাহলে তুমি দেখো ওভারঅল যদি ক্যালকুলেট করো তাহলে কত থাকার কথা, 360। সেটা হচ্ছে কি হচ্ছে না তুমি সেটা দেখতে পাবে নিচে থেকেই, ঠিক আছে। ফেজ এর জন্য
ওকে
আমার এখানে যে ছবিটা দেওয়া আছে ফর ফেজ এ, সিমিলারলি ফেজ বি থাকবে, সিমিলারলি ফেজ সিও থাকবে। এখানে ছবিটা সিম্পলিফিকেশনের জন্য শুধু ফেজ এটা দেওয়া আছে। ওকে, সো এটা ভাবো না যে ফেজ বিটা থাকবে না, অবভিয়াসলি ফেজ বিরও থাকবে, এখানে ফেজ সি এরও থাকবে, কিন্তু জাস্ট ফর সিম্পলিফিকেশন we have it only for phase A has been shown, ঠিক আছে। ওকে, নাও অ্যাজ ইউ ক্যান সি
ওকে স্যার
রোটারে যেমন স্লটস ছিল, আর্মেচারেও কিন্তু সেরকম স্লটস আছে। সো দিস আর দ্য স্লটস ফর এসি আর্মেচার ওয়াইন্ডিং। ওকে, দিস আর দ্য স্লটস ফর এসি আর্মেচার ওয়াইন্ডিং। ওকে, তাহলে এদের ইন্টারাকশনেই এই এয়ার গ্যাপে কি হচ্ছে, এই এয়ার গ্যাপে কিন্তু আমার ওই রোটেটিং ম্যাগনেটিক ফিল্ডটা প্রডিউসড হচ্ছে। ওকে, দ্যাট রোটেটিং ম্যাগনেটিক ফিল্ড will be produced. Now the magnetic axis of the rotor field winding is referred to as the D axis or the direct axis. Okay, the magnetic axis, please remember this, that the magnetic axis of the rotor field winding is referred to as the direct axis, and perpendicular to the D axis is the quadrature axis. Okay, perpendicular to the D axis is found the quadrature, also known as our Q axis. Okay, now the rotor winding is so arranged on the rotor periphery that the field excitation produces nearly sinusoidal distributed flux per pole in the air gap. তাহলে কি করছে, rotor winding is so arranged on the rotor periphery, means it is the rotor is so arranged on this periphery that what will happen, that the field excitation produces nearly sinusoidal distributed flux per pole, প্রায় nearly sinusoidal flux per pole ওই এয়ার গ্যাপে তৈরি হবে, and that value is how much, that value is our phi f. Okay, similarly when we're talking about the stator, so the stator has balanced three phase windings, a prime, b prime, c prime. I think here as you can see in this figure, a prime, b prime, c prime. Okay, so they have balanced three phase phases. Okay, and the rotor and what is happening for the stator, so the winding shown in this figure actually is shown a concentrated one, but actually it is distributed across the stator periphery. এখানে যেহেতু ফেজ এর জন্য দেখানো হয়েছে, only it is showing for phase A, that's why it is showing to be concentrated, but actually it is distributed around the periphery of the stator. Okay, here it is মানে পুরো এই জায়গাটাই কিন্তু আমার এরকম ডিস্ট্রিবিউশন আছে। ওকে, সো the winding in an actual machine is distributed across the stator periphery. So the stator winding or the armature winding is placed in equidistant slots which are located around the total inner stator surface. Okay, so the armature winding is placed in equidistant slots which are located around the total inner surface, around this total inner surface of the stator. Okay, so the armature is divided into three identical phase windings, as we are saying that a prime, b prime, c prime. Okay, so the armature is divided into three identical phase windings which are placed in 3p phase belts. Okay, তোমার প্রশ্নের উত্তরটা তুমি কিন্তু এখানে আবার পাচ্ছ। Okay, so the phase windings are placed in 3p phase belts, so each of which spans how much, 120 by p degrees of the stator সারফেস। ওকে, তাহলে কতগুলো, তাহলে যেহেতু আমরা টু পোল মেশিন ইউজ করছি, সো ইন দ্য টু পোল মেশিন দেয়ার উইল বি এ টোটাল অফ, তাহলে কতগুলো ফেস বেল্টস হবে, 6 belts of each spanning 60 degree. Okay, so there will be 6 belts each spanning 60 degrees. So as you can see from here, we are showing here only for phase A. So this is for phase A, this is for phase A. Similarly, there will be for phase B, phase C, and so on. Okay, and see, this is the rotor field axis or the magnetic axis of the rotor, and this is known as our d axis. Okay, here it is written as the d axis. So this line is the magnetic field axis of the rotor. So this is known as our d axis, and perpendicular to it is the q axis or the quadrature axis. তাহলে যেই তাহলে যে রোটারে যে phi f produced হচ্ছে, this will be produced in this direction along the magnetic field axis of the rotor, around the magnetic axis of the rotor field winding. Here this phi f would be produced. Okay, এটার proportionally phi f will be produced. Okay, so
এক্সকিউজ মি স্যার,
yes,
কেমন একটা হিসিং সাউন্ড আসছে স্যার আপনার
ও
মাইকটাতে।
এইবার ঠিক আছে, কারো তাহলে একটা জেনে মানে কারো একটা মাইক্রোফোন অন ছিল। ওকে,
ইয়েস স্যার।
এবার ঠিক আছে তো?
স্যার এখনো আসছে।
হচ্ছে এইবার আমার মনে হয় এখন ঠিক হয়ে গেছে। আমার কাছেও আসছিল, আসলে কারো একটা মনে হয় মাইক্রোফোন অন ছিল। ওকে,
ওকে স্যার।
স্যার একদম ফার্স্টে আমার অন ছিল, কিন্তু এখন অফ করে দিয়েছি।
ঠিক আছে। Okay, so as I was saying,
স্যার এখন ঠিক হয়ে গেছে।
okay, as I was saying, so the armature is divided into three identical phase windings which are placed in 3p phase belts. তাহলে যেহেতু two pole machine use করছি, so there will be 6 belts each spanning 60 degree. Okay, so the three identical phase windings are interconnected to form a generator neutral, which is normally grounded. So obviously this is how the stator is obviously there. So here the induced voltage is produced. So all the three terminals are joined together to form a neutral, which is normally grounded. So the three identical phase windings are interconnected to form a generator, which is to form a generator neutral, which is normally grounded. Okay, so what happens? So as the rotor will be rotating, the three-phase EMFs are produced in the stator winding. Okay, so as the rotor rotates, three-phase EMFs are also produced in the stator winding. ঠিক আছে? So আমি এই স্লাইডটা স্কিপ করছি because I think you know that that theta equal to p by 2 theta m, that if is this is the relationship between the electrical and the mechanical units of an angle. আশা করি সেটা জানো তো, that theta electrical
Yes,
equal
sir.
to p by 2 into theta m. আমি সেটা কিভাবে আসছে সেটা এখানে দেওয়া আছে, সেটা তোমরা জানো বলে আমি এটা স্কিপ করে যাচ্ছি। ঠিক আছে, and how this equation is coming, I think from this equation very easily we can deduce this particular equation, that is f equal to 120 or sorry, n equal to 120 f by p. Okay, we know this one, so I'm skipping this. So okay, what I was saying in the last part, I was saying that as the rotor rotates, the three-phase EMFs are produced in the stator winding. So obviously the interaction between the stator is the three-phase EMFs in the stator winding as well as the field MMF. Okay, these two would be interacting to produce our means the resultant of these two should be the voltage, induced voltage in that we are getting across the stator windings, তাই তো? তাহলে দেখি কি how it is actually being done, okay, or how it is formed. So আমরা প্রথমে assume করে নিচ্ছি কি, so we are assuming a cylindrical rotor synchronous generator. Okay, we are assuming on a synchronous cylindrical rotor synchronous generator, and since the machine is a balanced one and a balanced loading will be considered. Okay, so what we have assumed that the machine is a balanced one and a balanced loading is considered, and that's why it can be modeled on a per phase basis, and what we have done for the reference phase A. Okay, now on no load, what is happening, that the voltage EF induced in the reference phase A lags 90 degree behind our phi F which produces it. Okay, please note again that the voltage EF induced in the reference phase A lags 90 degree behind our phi F which produces it, and is proportional to it if the magnetic circuit is assumed to be unsaturated. মানে phi F যদি বাড়বে EF টাও কিন্তু বাড়বে, phi F যদি বাড়ে EF টাও বাড়বে। Okay, we can assume this one. Now since we are assuming that a balanced steady load is drawn from the stator winding, so the stator currents produce synchronously rotating flux per pole. Okay, so the stator currents produce synchronous rotating flux per pole that is phi a per pole in the direction of rotation of the rotor. Okay, in the direction of rotation of the rotor. Now this flux is called the armature reaction flux. Okay, this flux, that is phi a per pole, this flux is called the armature reaction flux and is therefore stationary with respect to the field flux. মানে field flux এর সাথে certain একটা অ্যাঙ্গেলে থাকবে এই armature reaction ফ্লাক্সটা, and that will always be stationary with respect to the field flux. মানে field flux আর armature reaction ফ্লাক্সের মধ্যে যে অ্যাঙ্গেলটা সেটা সবসময় সেম থাকবে। Okay, and since this armature reaction flux is being produced by the stator currents flowing through the stator windings, so this phi a is in phase with the phase A current IA which causes it. Okay, so IA current টা তৈরি করছে armature reaction flux phi A, and that's why phi A is in phase with the phase A current IA which produces it. এত অবধি clear? এত অবধি clear? Okay, so
Yes, sir.
since what we are again assuming, we are assuming that the magnetic circuit is assumed to be unsaturated. Okay, we are assuming that the magnetic circuit is assumed to be unsaturated, so we can actually apply the superposition principle and we can find that the resultant air gap flux is given by the phasor sum phi r equal to phi f plus phi a. So what we are neglecting, please note that we are neglecting the armature leakage reactance and resistance, and obviously this phi r is inducing the armature EMF which equals the terminal voltage Vt that we are getting across the generator. Okay, so phi r is inducing the armature EMF which equals the terminal voltage Vt. Okay, so this phi r is the resultant air gap flux which is being induced, which is inducing the armature windings, which induces the armature EMF which equals the terminal voltage Vt which we are getting across the generator. So তাহলে আমরা তাহলে এটাকে কিভাবে দেখতে পারি? Let us see with respect to a phasor diagram. Okay, so now what we're doing, we'll be drawing the phasor diagram of the generator operation. So first of all, we can think of it in this way. So the phasor diagram of a generator operation for the cylindrical rotor synchronous generator. So what we are seeing that first of all we can just for a cylindrical rotor আমরা এইভাবে ধরতে পারি, two pole rotor আছে। So this is the DC field winding here, as you can see. This is the DC field winding. Okay, this is the DC field winding, and this is the current I, and this is the flux phi f. Okay, so flux phi f is in what? Flux phi f basically is in the direction of the magnetic field of the magnetic axis of the rotor. Correct? So that is our dx. আর ঠিক ওর অপোজিটে কি হচ্ছে? ওর 90 degree perpendicular কি থাকছে? আমার qx. So as you can see, what we have here, so what we have here, this is our phi f. Okay, this is our phi f, as you can see here, and this phi f is in proportional to the d axis. তো ঠিক phi f এর 90 ডিগ্রিতে কি আছে? 90 ডিগ্রিতে আছে হচ্ছে আমার q axis. Okay, that is our quadrature axis. Now phi a, আর আমরা কি ধরেছি? আমরা ভোল্টেজটাকে যদি রেফারেন্স ধরি, okay, what we have taken as this voltage Vt as the reference. See, we have taken this voltage as Vt as the reference. Okay, so this voltage Vt has been taken to be the reference. This voltage, as you can see here. Okay, this voltage is the reference. So this is Vt. Vt কে কে ল্যাগ করছে? Current Ia. Okay, so current Ia যদি এই দিকে হয়, আমরা কি দেখলাম? That the armature reaction flux is in phase with the current. So Ia যদি এই দিকে হয়, the armature reaction flux would also be in the same direction. So this is the armature reaction flux. Okay, so this is our phi a, as you can see here. Now as I was saying, that this particular angle, okay, this particular angle between phi f and phi a will always be remaining constant. Okay, this particular angle will always be remaining constant. So what we are seeing, that if this is phi f, this is a phi a, so phi r is the resultant of phi f plus phi a. So this is our phi r. As you can see, this green line is our phi r. Okay, let me just write it down in yellow. So this is our phi r, as you can see here. Okay. So this yellow line is our phi r. Okay. So as you can see, so what we can, so এটা যদি 90 degree হয়, so we have, so this is the angle actually between phi f and phi r. What angle? This angle is known as our load angle. Okay, this angle delta is known as our load angle. So this angle delta can be known as you can see here, it is written, this angle can be known as our power angle, load angle, torque angle, and again this delta can also be regarded as the angle between the resultant magnetic field and the field flux. Okay, between the resultant magnetic field and the field flux. So this is our angle, that is our delta. তাহলে তুমি যদি ইকুয়েশনটা মানে এই টোটাল ইকুয়েশনে দেখো, so we can also say if this is delta, then this angle can also be said to be equal to delta. That is, the angle between EF and VT can also be said to be equal to delta. Similarly, এই যে কারেন্টের ভ্যালু, এটাকে যদি আমরা এক্সটেন্ড করি, তাহলে অ্যাকচুয়ালি ইফ মিনস we can do, we can just complete the phasor. So if we want to complete the phasor, so I এর perpendicular কি থাকবে, আমার j axis থাকবে. What is j axis? j axis হচ্ছে আমার synchronous reactance, that is equal to actually the armature reactance plus the armature leakage reactance. Okay, so what we can say, so that would be perpendicular to the current value IA. So that is what we are seeing. Okay, so what we can say then, so phi f is our field flux, phi a is the armature reaction flux, phi r is the resultant flux, EF is the generated voltage, the voltage that is being produced, VT is the terminal voltage. Okay, delta is the power angle or the load angle or the torque angle, and XS that we are saying, that is the synchronous reactance. Okay, ঠিক আছে, এত অবধি বোঝা গেছে? Any
Yes, sir.
questions now? Okay, so what we can do now, that since we have drawn the phasor diagram, so we can actually then find the equivalent circuit model of the cylindrical rotor synchronous generator also. So this is the equivalent circuit model of the cylindrical rotor synchronous generator. Please again note again that what we have assumed that the synchronous generator is connected to an infinite bus, and that's why the VT is having a value of VT angle 0 degree. Okay, so what we are seeing, that the synchronous generator is connected to an infinite bus. So EF is our no load induced EMF. Okay, as you can see, EF angle delta is, this is our excess.
এক্সকিউজ মি স্যার,
হ্যাঁ?
আমাদের কি ফেজার ডায়াগ্রামস বানাতে আসতে পারে?
হ্যাঁ, আসতেই পারে,
ওকে
আসতেই পারে, না আসার কিছু নেই। না তোমরা কিভাবে এসছে সেটা বুঝতে পেরেছো না? আমি আবার এক্সপ্লেন করব।
স্যার আমার ওই ভিটি না, মানে এই পার্টটা খালি ভিটিটা রেফারেন্স হিসাবে ধরে, তারপরে ওই আই এটা যেটা আসলো,
Okay.
তারপরে ওইটা একটু ওই পার্টটাই একটু, মানে ফাইয়ের পার্টটা বুঝতে পেরে গেছি, ফাই
আন্ডারস্টুড। তাহলে আমি একটু পরিষ্কার করে আর একটু করে ফেলি, তাহলে তুমি আর একটু বুঝতে পারবে। জাস্ট ওয়েট। ওকে, let me just add another page. Yes, okay, আমি আবার বলছি, আমি প্রথম থেকে করছি তাহলে, ঠিক আছে? So what we are getting, so we are taking VT as the reference here, VT, ঠিক আছে? And this is our current IA, that is actually মানে এইটা হচ্ছে আমার টার্মিনাল ভোল্টেজ যেটা আমরা পাচ্ছি, কারেক্ট? Yes, okay, so if this is our phi f, তাহলে VT যদি এটা হয়, তাহলে phi r টা কি হবে? Something like this.
ইয়েস স্যার।
This should be our phi r. Okay, that is because this is the resultant field flux which is actually inducing this terminal voltage VT. VT is the terminal voltage, no?
ইয়েস স্যার,
That we are
ওটাই
getting
স্যার।
across. Okay,
ইয়েস স্যার।
and this is IA is the current flowing through phase A. ঠিক আছে?
ইয়েস
আমরা তো
স্যার।
পার ফেজ বেসিসে করছি with respect to phase A, ঠিক আছে? তাহলে এটা যদি হয় তাহলে what was our phi f? Phi f টা কি হবে with respect to d axis?
স্যার ফার্স্ট তাহলে আপনি আঁকছেন,
ঠিক
ফার্স্ট
আছে,
আঁকছেন ভিটিটা, তারপরে আঁকছেন ফাই আরটা।
কারেক্ট, ঠিক আছে। সো ইফ দিস ইজ phi f, সো এই phi f এর সাথে i এটা কি প্রডিউস করছে? The current
স্যার
is
তারপরে
producing the
সেটা বানাচ্ছে
armature,
ফাই
yeah,
আর।
that is producing the armature reaction flux, that is phi a. Okay, ia is producing the armature reaction flux phi a. Okay, and
Yes,
phi
sir.
a is in phase with ia. That's why if this is the direction of ia, the phi a direction would be this. Understood?
Yes, sir.
Okay, so this is our fire. ফায়ারের জন্য ভিটি তৈরি হচ্ছে। ওকে, এবার খেয়াল করে দেখো, if this is the case, if this is our d axis that we have just said, so d axis এর perpendicular কি থাকবে?
কিউ অ্যাক্সেস।
q axis, correct? so এখানে যদি phi f হয়, phi f তাহলে কি প্রডিউস করছে?
EF.
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 so this is our ef. okay,
ও
again
স্যার,
please note,
পারপেন্ডিকুলার গুলোকে ওই একই কালারে আপনি রিপ্রেজেন্ট করে দিচ্ছেন, মানে কোনটা কিসের জন্য রেসপন্সিবল।
ওকে,
হ্যাঁ হ্যাঁ,
ঠিক আছে।
ইয়েস স্যার, ইয়েস স্যার,
ওকে,
ইয়েস
সো
স্যার, ইয়েস
phi f যত বাড়বে ef তত বাড়বে। ওকে, এবার সিস্টেমে কি আছে? রিঅ্যাকট্যান্স আছে। কি রিঅ্যাকট্যান্স আমি বললাম? একটা হচ্ছে
সিনক্রোনাস রিঅ্যাকট্যান্স।
synchronous reactance, that is the summation of xa plus xl, that is xa armature reaction reactance, xl
আর
হচ্ছে
লিকেজ
armature leakage reactance.
রিঅ্যাকট্যান্স।
So that will always be তোমার in quadrature with the current value. Okay, if that is the case, তাহলে এটা যদি কারেন্ট হয়, so they would obviously be in quadrature with the current value. ছবিটা ঠিক ক্লিয়ার হচ্ছে না? বুঝতেই পারছো যে this would be in quadrature. Okay, so this value should be this portion that we're talking about. This is how much then? This should be j into ia into xs. Because of the quadrature, this j term is coming, correct? So
Yes,
this
sir.
is vt and xs, vt plus j into ix. So ef angle delta should be equal to vt plus j into vt plus j into i into xs. কি তাই হওয়া উচিত তো?
Yes, sir.
ef should be, or
V-
ef angle
VT
delta,
plus JIXS.
okay?
Yes, sir.
So we are drawing this one in our equivalent circuit here. Understood?
Yes, sir.
Okay, this is what we are getting. Please again see that we are maintaining this, that the synchronous generator is connected to an infinite bus. What type of synchronous generator? A cylindrical rotor synchronous generator.
Yes,
Okay.
sir. Yes, sir.
So the power delivered is how much? So the power delivered at the output কি আমরা পাই? S, তাই তো? So S is equal to how much? So the power delivered at the generator terminal is equal to P plus JQ. Okay. So what is the convention? P plus JQ equal to VT into I conjugate. Yes? Now
Yes,
I
sir.
would ask,
Yes,
I
sir.
would ask you a question. Why I conjugate?
Sir,
Inductive
because
power positive.
inductive
Inductive power is
power.
taken to be positive. Okay, that is the convention. So we'll
Yes.
be putting this value of I from here into this equation. কি লিখতে পারি তো? আগের থেকে এইখান থেকে I কে কি লিখতে পারি? We can write I in this way.
Yes, sir.
So we are putting it in this expression, and if we solve it, I would ask you to solve it, then we'll be getting that P equal to EF into VT by XS sin delta, and Q equal to VT by XS into EF cos delta minus VT. So আগে যে আমরা যে ইকুয়েশনটা বার করেছিলাম আগের দিনে, so are we not getting more or less same type of equation? Are we not getting the same type of equation where we are seeing that as delta is in, if you remember this figure, as delta is changing, P value is also changing. As VT value is changing or the voltage value is changing, the reactive power part or the portion is changing. Correct? Okay. So the active here. change in P affects the perpendicular component of the voltage drop, and change in Q affects the in-phase component of the voltage drop. The same thing can be seen in this expression also, where we are seeing that our P is equal to EF Vt by Xs sin delta, and Q is equal to Vt by Xs EF cos delta minus Vt. So we can say that P and delta, okay, what we can say? We can say that P is proportional to delta and Q is proportional to voltage. Okay, so if we want to control the active power, so we have to control the delta and vice versa. Similarly, if we have to control the reactive power, we have to control the voltage. Okay, the same concept that we have applied for our cylindrical rotor synchronous generator, that also can be applied for a typical transmission line. Okay, that can also be extended to a typical transmission line. আমরা cylindrical rotor কি বার করছি? No load induced EMF EF into VT, that is the terminal voltage of the synchronous generator. Okay, here. Okay, but in transmission line, what it would be? It would be V1 and V2, that is sending end and receiving end. And in transmission line, again, what we have taken? We have taken the impedance to be equal to the X or the reactance value. Why? Because the X by R ratio of a transmission line is very high. Why the X by R ratio of a transmission line is very high? Because we know that in a transmission line, we are using what type of voltages? Very high voltages. So because of which the inductance value, because of which the distance between the conductors has to be higher. So 2 equal to 2 into 10 to the power minus 7 ln how much? D by R prime, no? Where this D is the distance between the conductors. So because of use of high voltage, the distance between the conductors is increasing, because of which the L value is increasing. So if the L value is increasing, so our X value also increases. So X by R ratio is much higher, and that's why what we take, we neglect the value of R in our calculations for a transmission line. Understood? And in a transmission line, the delta angle. So why the so many names of the delta angle? I think you are getting the point, because with respect to the transmission line, we can say it be a power angle or our load angle, whereas with respect to our cylindrical rotor synchronous generator, this delta angle is normally known as a torque angle, because it is basically the angle between what and what? Basically, it can be regarded as the angle, oh, that has been removed from here. Delta is the angle between the
phi f.
Yes, between the resultant magnetic field and field flux. And that's why so many names of our delta. Understood? Okay.
Yes, sir.
Now, what's the time? Yes, 15 minutes left. So now what we're talking about, we'll be talking about the active variation of the power. First of all, what we'll be taking into account? We are taking into account active power variation, and the next case we're talking about reactive power variation. Now, when we're talking about active power variation, the things that we have kept constant, as you can see from the figure, that we have taken that Xs is constant. That is our synchronous reactance that has been taken to be constant, and that is, and why it can be taken to be constant? Because it depends on the design parameters. Okay, similarly the Vt is constant because we are assuming that the synchronous generator is connected to an infinite bus. Okay, now what we know that EF, that is our no load induced EMF, is proportional to phi f into omega r, where omega r is the speed of the rotor, and the speed of the rotor is a constant value. So omega r is constant, so we can say EF is proportional to phi f. Again, phi f is proportional to what? Phi f is produced by IF, that is the field current. So we can say that since IF is produced, we can say that since phi f is produced from IF, so we can say EF, that is the no load induced EMF, is proportional to our field current IF. Now this field current that we are talking about, this itself is produced from the exciter of the synchronous generator. So if that is the case, so in this expression of P equal to EF Vt by Xs, we can take each of the elements to be a constant if we assume that the field is also constant. Okay, so keeping the field excitation or the field constant, the active power is given by P equal to P max sine delta. So what we can say, where this P max is equal to EF Vt by XS. Okay, so we can say that P is proportional to our delta or the load angle, where we can say in this way also that if P varies, then delta also varies. Okay, so the graphical representation of P versus delta, okay, this P, that is PE here, means the electrical power, okay, electrical power output. So the graphical representation of PE versus delta curve, this curve is known as our power angle curve. Okay, so please remember that this curve is actually known as our power angle curve. Why it is useful? It is useful because this curve is widely used in power system stability studies, as we'll be seeing later when we'll be talking about our uh, when we're talking about power system stability. We have a separate chapter dedicated to it. Now, as you can see that this particular curve is achieving its maximum at delta equal to 90 degree. Okay, so this portion P max, so the values up to delta equal to 90 degree, this region, okay, this region is known as our stable region, and the other region, okay, is known as our, this region is known as our stable region, and the other region is known as our unstable region. Okay, this region is known as our unstable region. Similarly, so if this is the case, then what we can do is that we can actually find 2 points. Okay, what are the 2 points we are seeing? As you can see, we have taken P0 here. Okay, this, sorry, this P0 is the mechanical input power to the synchronous generator. Okay, so if P0 is the mechanical input power to the synchronous generator, so if this is kept constant, so with respect to this power angle curve, so the points where this power angle curve actually intersects this mechanical input power line, we can see that there are 2 points. What are the 2 points? Number point A is known as our stable operating point, as you can see here, and number P is known as our unstable operating point. So this point is unstable operating point, and this point is our stable operating point. Now the question comes, why this is stable and why this is unstable? Okay, the what I will do is that I will be just briefly explaining it. Okay, we'll be talking about it in details when we're talking about it in our stability classes. So এই class I'm just briefly explain করছি. Okay, so suppose what happens that the input power, okay, so the input power to the generator has been increased. Okay, so if P1 is increased, ঠিক আছে, P1 is increased in such a way, so what can happen then, if delta 0 was the previous operating point, so কি হচ্ছে এখন এই অপারেটিং পয়েন্টটা কিন্তু জাম্প করে এইখানে চলে আসার কথা, তাই তো? So that the condition that PM is always equal to PE, so there is a stable condition should always be maintained. Sorry, PM, yes, or we can write P0. Okay, that is P0 is equal to PE. This condition is always maintained. Okay, এইবার এই কন্ডিশনে যদি আমার P0 থেকে P1 হয়ে যায়, তাহলে অপারেটিং পয়েন্টে তাহলে P1 equal to PE হওয়ার কথা ছিল। Okay, it should have been the case, but what happens is that whenever there is some accelerating energy in the system, so what will happen that this point will go on accelerating in this path. Okay, but it should have stopped at this point when the mechanical input power is equal to the electrical output power, correct? But it will not stop at this point. Why? Because of the inertia of the synchronous generator. Okay, because of the inertia of the synchronous generator. So due to the inertia of the synchronous generator, what will happen that this operating point will overshoot this point. ঠিক আছে, ওভারশুট করে গেলে কি হবে? সো ওভারশুট করে গেলে এইবার তুমি দেখো যখনই ওভারশুট করে যাচ্ছে, then the electrical power output is more than the mechanical power input. কারেক্ট? এই পজিশনে সাপোজ এত অবধি ওভারশুট করছে, ঠিক আছে, আপ টু হিয়ার ওভারশুট করলো, লেট দিস পয়েন্ট বি আওয়ার ডি পয়েন্ট, ঠিক আছে, এই ডি পয়েন্টে অবধি যখন ওভারশুট করলো, সেই ডি পয়েন্টে দেখা যাচ্ছে দ্যাট দ্য মেকানিক্যাল পাওয়ার ইনপুট কত এখন? P1, the mechanical power input is less than the electrical power output. Yes or no?
Yes, sir.
Yes, sir.
Yes,
Okay,
sir.
So what will happen then? But our mechanical input power তো fixed আছে এই P1 এ. What will happen that the operating point will be
স্যার আবার
decelerating.
ডিসেলারেট করবে,
ডিসলেট
crack
করবে, করে ও আস্তে আস্তে এখানে কিন্তু স্টপ করে যাওয়ার কথা ছিল at point C. It should have stopped at point C, but again it is not stopping at point C. Why? Because there is inertia in the system. Okay, so it will again overshoot. So we know that the system is having certain type of damping, correct? So because of which ultimately what will happen, that it will oscillate around this point and then it will settle down at this point. So what we are seeing, that the system stability is not being hampered, system is okay. Okay, now with respect to this position আমরা যদি ভাবি, with respect to this point, same condition P1 যখন আমরা ইনক্রিজ করছি, what is happening, দেখো এইখানে আমরা দেখতে পাচ্ছি কি, that the operating point was at this point. Yes, তাই তো? Yes, অপারেটিং
Yes, sir.
পয়েন্টটা প্রিভিয়াসলি এখানে ছিল, এইবার
Yes, sir.
অপারেটিং পয়েন্টটা এখানে আসার কথা, ঠিক আছে? কিন্তু
Yes, sir.
খেয়াল করে দেখো, ইন মেকানিক্যাল ইনপুট পাওয়ারটা যখন বাড়িয়ে দিয়েছি, P1 is max, what is the electrical power output corresponding to this position B? Is it more or less? Less?
Yes, sir. P1 টা বাড়িয়ে দিয়েছেন, মানে মেকানিক্যালটা বাড়িয়েছেন, তাহলে তো
Mechanical input powerটা, whatever the electrical power output which corresponding to position B, it is less?
Yes, sir.
Less, sir.
ঠিক তো? এবার যেহেতু less, what will happen? There will be acceleration in the system. ঠিক আছে?
Yes, sir.
So when the mechanical input power is more, electrical power output is less. So the electrical power output will try to make itself equal to the mechanical input power. Means more mechanical input power, more মানে কি? The turbine will move faster, so that more amount of steam is being allowed to the generator, so that the electrical power output increases. Correct? Yes or no?
Yes, sir.
Yes,
Yes,
sir.
sir.
But corresponding to position B, if more amount of steam is being applied, delta value is what? Delta value is increasing.
Yes, sir.
So what will happen? That it will be losing out of synchronism. Okay, because delta value to amar to delta ke edige kombe? No, it will increase in this way. Right? So because there is a difference between the electrical power output and the mechanical power input at corresponding to this particular position. Understood what I am saying?
ডেল্টার ভ্যালুটা আরো বেড়ে যাবে।
Delta value বাড়বে. So what means?
Yes.
Means the system will be out of synchronism. At what point? At point B. Understood? Because they means it would be a runaway situation. ডেল্টাটা আমার বেড়েই গেল। তাহলে তুমি একটা ভাবো যে দুটো কাপলিং ছিল, হট করে একটা কাপলিং জোরে ঘুরতে শুরু করলো, অন্যটা কিন্তু অত স্পিডে যাচ্ছে না, তখন কি হবে? কাপলিংটা কি হবে? The coupling will open, and that is what means there is no synchronism between them, and that is what will be happening here. Understood? And that is what we'll be saying, and that is why we
Yes,
are
sir.
saying that the point B is an unstable operating point. We'll be again talking about in details in our power system stability classes. Understood? So what we can see is that the output is actually will be following the input. Input কতটা চেঞ্জ হবে তার উপর কিন্তু আউটপুট ডিপেন্ড করবে। Rather we can say it in other ways also, in vice versa বলতে পারি, যখন আউটপুটটা চেঞ্জ করবে ইনপুটটাও কিন্তু সেভাবে কিন্তু চেঞ্জ করবে। Okay, why? Because I have a slide here. Let us see this one, then again it will be more clear what I've just said. Okay, here see the operation of the synchronous generators. See, the synchronization can take place if the following conditions are satisfied. What are the conditions? The generator and network frequencies are equal. Phase sequence of the generator matches that of the network. The generator EMF and the network voltage are of equal magnitude, and they are also should be of the equal phase. So once a generator has been synchronized onto a network, electromechanical forces build up in the machine and then tend to keep it running at the same speed as the rest of the network. Network এর যা speed সেটাও generator speed হবে. Once the speed of the generator is locked to the rest of the system, we may control its real power generation by controlling the torque from its prime mover. টর্কটা কন্ট্রোল করছি, মানে আমরা কোনটা কন্ট্রোল করছি? What is we are controlling?
Mechanical
Delta control
inputting
করছি,
power.
correct? We are controlling the delta value. So if we control the delta value, the real power can also be controlled. Okay, how it is controlling? We are opening the steam valve, increase in the steam pressure. If you open the steam valve, there will be increase in the steam pressure on the turbine blades. So we are applying greater torque to the generator, thereby tending to accelerate the generator. But what we are saying? We are saying that the speed of the generator is locked to the rest of the system. But again also we are saying that the generator is accelerating. Okay, what do you mean by that? Since the speed is tied to the rest of the system, what happens is that the rotor advances its running angle a few degrees. Okay, so if so মানে কি এবার তুমি বুঝতেই পারছো যে রোটারটা কিছুটা মানে ওই যে ডেল্টা ভ্যালুটা কি হলো, ইনক্রিজ করে গেল। ওকে, so what will happen? This results in an increase in delivered current and power. At the same time, the current will be building up an decelerating torque within the machine that exactly counteracts the accelerating torque. Okay, so within each generator we thus have a delicate automatic torque balancing mechanism. If all the generators have a perfect torque balance, their speed and thus the frequency remains constant. But there will be fluctuations in the system load which are very random in nature, and it is impossible to accomplish a perfect instant by instant match between the generation and demand, and that is what we are seeing in our load curve. Correct, but that is what we are seeing in the load curve. The power ta sob shomoy with time kintu vary korche. So let us consider what would happen if we are running at 50 hertz perfectly power matched and there a sudden load drop is experienced. So what will happen? That the prime mover valve settings will remain unchanged, meaning the drive torques are unchanged. মানে mechanical input powerটা কিন্তু সেম আছে, আউটপুট পাওয়ারে কি হয়েছে, আউটপুটে মানে লোডে সাডেন লোডটা ড্রপ করে গেছে। সো দ্য ডিক্রিজ ইন দ্য লোড রেজাল্টস ইন এন কারেন্ট decrease which will be distributed among all the generators, resulting in a slight decrease in the electromechanical torques in each machine. So every generator would experience a small surplus accelerating torque with an ensuing speed, and obviously the frequency will also increase. So the rate at which the speed and obviously the frequency increase depends upon the total moment of inertia of the running equipments. We'll be talking about it later as we progress. Okay, so as you can see that all the thousands of motors which during these moments were being supplied by the network would likewise experience increase in frequency. মানে যে নেটওয়ার্কে যেহেতু সারপ্লাস অ্যাক্সিলারেটিং টর্ক আছে, তার জন্য কি হবে, নেটওয়ার্কের সিস্টেম ফ্রিকোয়েন্সিটা ইনক্রিজ করবে। যদি সিস্টেম ফ্রিকোয়েন্সি ইনক্রিজ করে তাহলে যতগুলো ইলেকট্রিক্যাল মোটর কানেক্টেড ছিল সবকটারে কিন্তু কি হবে, সবকটারে কিন্তু ফ্রিকোয়েন্সিটা ইনক্রিজ করবে। ফ্রিকোয়েন্সি ইনক্রিজ করা মানে কি, the speed of those motors would go up and they would meet all the higher load torques. So since they are meeting higher load torques, that means that the motors will be pulling more power from the network. So the resulting load increase would soon balance out the load decrease, and the frequency would level off to a new value. Okay, so the resulting load increase would soon balance out the load decrease that started this chain of events, and the frequency would level off to a new value. কিন্তু আমরা দেখব যে this is what actually happens, but in real life actually the prime mover settings আমরা কি বললাম এখানে, the prime mover valves will remain unchanged বললাম তো, that will not remain unchanged, but rather they will change in phase of shifting frequency. Okay, they will change in phase of shifting frequency. Any questions till now?
স্যার তার মানে সিস্টেমে কানেক্ট
স্যার এই মানে এই শিফটিং ফ্রিকোয়েন্সিতে তাহলে লোড ড্রপ হয়ে গেলে তাহলে ফ্রিকোয়েন্সিটা তাহলে চেঞ্জ করছে, মানে বেসিক্যালি পুরো গল্পটার মানে
গল্প না, মানে থিওরিটা,
মানে পুরো থিওরিটা যেটা
এক্স্যাক্টলি। সো হোয়াট উই আর অ্যাকচুয়ালি, আমি আরো সিম্পল ভাবে বলছি। ইয়েস, আর জন্য কি কারো একটা প্রশ্ন ছিল, কি বলছিলে কেউ?
স্যার তার মানে যে মোটরগুলো সিস্টেমে কানেক্ট রয়েছে তারা অ্যাকচুয়ালি সিস্টেমের স্টেবিলিটি ইনক্রিজ করছে।
কারেক্ট, কারেক্ট। ওকে, সো আমার যদি সিস্টেমে লোড ড্রপ হয়, সিস্টেমে তাহলে মোর অ্যামাউন্ট অফ অ্যাক্সিলারেটিং এনার্জি আছে, তো ইনপুট পাওয়ারটা তো আমার চেঞ্জ হয়নি। কারেক্ট, সিস্টেমে তো ইনপুট পাওয়ারটা তো ম্যাক্সিমাম
Yes,
আছে,
sir, তখন এই
যখন এই
লোড
লোড ড্রপ হয়ে যাচ্ছে তার মানে
হ্যাঁ,
সারপ্লাস এনার্জি থাকছে, সারপ্লাস এনার্জি থাকছে মানে কি সিস্টেমের ফ্রিকোয়েন্সিটা ইনক্রিজ করছে, কারেক্ট? ফ্রিকোয়েন্সি ইনক্রিজ করা মানে কি সিস্টেমে যে লোডগুলো কানেক্টেড আছে, অন্য লোডগুলো, অন্য ইলেকট্রিক মোটরগুলো, তারা তাদের স্পিডটা বাড়ছে, ফ্রিকোয়েন্সি ইনক্রিজ করছে মানে তাদের স্পিডটা বাড়ছে। তারা যদি স্পিডটা বাড়ায় তার মানে কি দে আর অ্যাচিং দেয়ার হায়ার লোড টর্কস। ইফ দ্যাট ইজ দ্য কেস দেন হোয়াট ডু মিন বাই দ্যাট? ইফ দ্যাট ইজ দ্য কেস we mean that they will be drawing more power from the network now. তার মানে কি ইনহেরেন্টলি তার মানে যে লোড ড্রপ হয়েছিল that would be balanced out by this load increase, correct? So ফ্রিকোয়েন্সিটা একটা নতুন ভ্যালুতে কিন্তু সেটেল ডাউন করে যাবে। কিন্তু we'll be talking about later when we're talking about in more details about this operation of synchronous generators, that these prime mover settings that we are saying that will remain unchanged, they actually does not remain unchanged. Okay, they change with change in frequency, with the shifting in frequency. Likewise, correction would be done in the prime mover valve settings also. Okay, সেখানে কিন্তু certain change হবে so that the frequency, কারণ আমাদের উদ্দেশ্যটা কি, that the frequency should be kept constant, correct? So the prime mover valve will be operating in such a way that the frequency tries to level off to a new value, that's the extreme case, or it remains constant. Okay, we'll be talking about it later in our later classes. Okay, yes, আপাতত ক্লিয়ার হয়েছে? তাহলে অ্যাক্টিভ পাওয়ার ভেরিয়েশনটা কিভাবে পাওয়ার অ্যাঙ্গেল কার্ভ আনছে আশা করি সেটা তোমরা বুঝতে পেরেছো। Yes?
Yes, sir.
So next what we're talking about the reactive power variation. Okay, we'll be talking about the reactive power variation. So when we're talking about the reactive power variation, so this is the equation that we'll be talking about. That is Q equal to Vt by Xs into EF cos delta minus Vt. So again, what we have assumed the same thing, that in reactive power variation we have assumed that the active power is the kept constant. Active power constant mane there is the turbine output. The turbine output is kept constant. So here also the equation we have Q equal to Vt by Xs EF cos delta minus Vt. So we are taking Vt equal to constant because what we have, this is connected to a infinite bus. That's why an Xs is constant because Xs is a design parameter. Okay. So what we have, so to change the reactive power, we have to vary the EF, that is the no load EMF, and that means that we have to vary the field current IF. Okay, we have to vary the field current IF. So let us see the phasor diagram. So we are talking about now the phasor diagram of a generator. Okay, phasor diagram of a generator. Obviously, we are talking about cylindrical rotor synchronous generator. Okay, of a cylindrical rotor synchronous generator. Okay, phasor diagram of a cylindrical rotor synchronous generator delivering constant power to an infinite bus with varying excitation. So কি দেখছি আমরা? So first of all আমরা দেখতে পাচ্ছি we have the terminal voltage Vt here. Okay, তাহলে ওর রেসপেক্টে আমরা কি করছি? First of all we are seeing, suppose EF1 দেখছি first of all, this black line. Okay, this black one line, follow this one. So এটা যদি EF1, so if this is Vt একদম perpendicularly, so if this is our and this is our delta 1, so এটার রেসপেক্টে EF যদি এই হয় তাহলে IF would be obviously in phase with our Vt. So this is our IF. Okay, similarly if this is our EF2, that is EF is much larger than Vt, as you can see here. If this is our EF2, so this is with respect to the EF2, if this is the line our Ji into Xs, if that is the case, then IF2 should be in this direction. And similarly, if this is our EF3, then our IF3 should be in this direction, that is perpendicular to this quadrature. Right? Okay, perpendicular to this phasor should be our IF3. So from this figure, what we can see that IF3 is less than IF1 is less than IF2. Okay, IF3 is less than IF1 is less than IF2. And similarly, what we have our delta 3 is greater than delta 1. Okay, is greater than delta 2. So as you can see that with the increase of the field current, the delta value is decreasing. Okay, with the increase of the field current, the delta value is decreasing, and vice versa. That is, your delta value increase করলে field current decrease করছে. But what we are seeing that this EF sin delta, this is obviously remaining constant. Okay, this EF sin delta is always remaining constant. Hence, what we can say that the reactive power is varying, but the active power output from the synchronous generator is remaining constant. Understood? Yes.
স্যার এখানে IF3 স্যার এটা কি করে আসলো IF3 less than IF1 less than IF2?
What we have done here is that we have tried to draw the phasor diagrams with respect to that. So IF মানে EF3 টা দেখো তুমি, EF3 ভ্যালুটা খুব কম, তাই তো, কম্পেয়ার টু EF1, ঠিক আছে? তাহলে EF3 ভ্যালুটা যদি কম হয় তাহলে
ও
এই
স্যার
যে
তাহলে ওটাই অ্যাজাম্পশনটা,
এক্স্যাক্টলি
ও
সেটাই তো আমি
ওটাই
বললাম।
ফার্স্ট অ্যাজাম্পশনটা, তারপরে তার জন্য ওই ডেল্টা ভ্যালু গুলো কি আসছে সেটা।
এক্স্যাক্টলি। Okay, so যখন field current increase করছে, so the what is happening that the delta value is decreasing, and vice versa. Means if delta value is increasing, as you can see, then the field current will be decreasing. Okay, so as you can see from the phasor diagram here that EF sin delta is kept constant, তাহলে আমাদের যে ইকুয়েশনটা থাকছে, that is our equation P equal to EF VT
স্যার
by
এরপরটা বুঝেছি
XS
স্যার
sin
এরপরটা
delta.
বুঝে গেছি স্যার।
Yes, that is always remaining constant, ঠিক আছে, because EF and sin delta, that is remaining constant, and VT and XS was constant from previous. So since the active power output from the generator is kept constant and its excitation is varied, so the armature current IA and its angle theta, that is the power factor, will change in such a manner so that the active power output remains constant. Okay, আমি আবার বলছি that since the active power output is kept constant and its excitation is varied, the armature current IA and its angle theta, that is the power factor, would change in such a manner to keep our active power output constant. So what is the active power output equation? That is mod VT into mod IA into cos theta. So this equation will always be constant. So with respect to this, actually, we can correspondingly draw three phasor diagrams. How? Correspondingly, three phasor diagrams showing how the variation of excitation results in change of power factor so that the active power output is kept constant can be shown. So what is the first case? First case is when EF cos delta is greater than our VT. So when EF cos delta is much greater than VT, so in this case, this is the phasor diagram, as you can see that EF cos delta is much greater than our VT. Then if this is the case, then in this condition we can see that the reactive power is positive. Okay, means the generator is supplying reactive power to the system. Okay, the generator is supplying reactive power to the system. And what type of reactive power? As you can see, it is positive. So the generator is supplying positive reactive power into the network. Yes. Yes.
Reactive power it is supplying, sir, to the positive reactive power, lagging reactive power from generator to load, sir.
Yes, it is supplying from power from the generator to the load. Okay, so the power factor is how much? Power factor is our lagging power factor. Okay, so this condition of the generator when EF cos delta is greater than VT, this is known as that the generator is in over excited condition. Okay, the generator is in over excited condition. Next, when we have EF cos delta is more or less equal to VT, that was our second equation here. As you can see, when EF cos delta is more or less equal to VT, when EF cos delta is more or less equal to VT, here the reactive power output from the generator is actually 0 and the power factor is unity, because the generator neither delivers nor consumes reactive power from the system. Okay, and the third condition that we can draw is that EF cos delta less than VT. Okay, that is our third figure here, where EF cos delta is less than VT. If EF cos delta is less than VT, then what would happen? Can anybody tell me? If EF
Sir, it consume reactive power.
It will be consuming reactive power from the supply. That is a very bad condition. That is known as the generator is under excited condition. ঠিক আছে,
And
it
power
is
factor will
starting
be
to
leading, sir.
power factor would be leading, correct. So as you can see here, power factor would be leading, reactive power is negative, that the generator is consuming reactive power from the supply. We always try to avoid this condition. Please remember this, okay, that the generator should always be supplying power to the network. It should not be consuming power from the network. That means that the generator there is some problem with the generator excitation. That is why we cannot ramp up the current value. No, because if the generator excitation is okay, then our means the AVRs, that is the automatic voltage regulators, if they are okay, then we can ramp up the IA. If I miss, we can ramp up the field current. If we can ramp up the field current, then the generator will be running in the overexcited condition, and the generator should be supplying reactive power to the supply to the system. Okay, so as you
Sir,
can, yes.
sir, in leading power factor, EF cos delta VT এর থেকে কম হবে।
হুম
তো স্যার এক্সাইটেশন যেটা ইএমএফ ইএফ সেটা তো ভিটির থেকে বেশি হলেও হতে পারে।
এক্সাইটেশনটা
হ্যাঁ
এক্সাইটেশনটা এক্সাইটেশনটা কম হচ্ছে বলে তো ইএফটা লেস হচ্ছে।
স্যার ইএফ কস ডেল্টা প্রোডাক্টটা ভিটির থেকে কম,
হ্যাঁ,
কিন্তু যদি আমি ইএফ ধরি এক্সাইটেশন ভোল্টেজ, সেটা তো মানে স্যার ম্যান্ডেটরি নয় যে ভিটির থেকে কম হবেই।
না না, কেন কেন ওটা সবসময় ম্যান্ডেটরি, এই কন্ডিশনে সবসময় কম হবে ইএফ কস ডেল্টা। এই কন্ডিশনে, আন্ডার এক্সাইটেড কন্ডিশনে তুমি দেখো, এখানে তো বোঝাই যাচ্ছে ইএফ কস ডেল্টাটা ভিটি থেকে কম হচ্ছে।
স্যার ইএফ কস ডেল্টা টোটাল মানে প্রোডাক্ট টার্মটা ইএফ ইন্টু কস ডেল্টা সেটা ভিটির থেকে কম হচ্ছে, কিন্তু এখান থেকে তো স্যার এটা বলতে পারছি না যে ইএফটাও ভিটির থেকে কম হচ্ছে, কম হবে।
দেখো
স্যার কস
ইএফ,
ডেল্টার টার্মটা ইন্ডিভিজুয়াল একের থেকে ছোট, তাই আমি ইএফ কে যদি
না না, তোমার
আহ,
তোমার প্রশ্নটা আমি বুঝতে পেরেছি, কিন্তু যখনই জেনারেটরটা রিয়াক্টিভ পাওয়ার কনজিউম করতে শুরু করেছে, ঠিক আছে, জেনারেটর যখনই রিয়াক্টিভ পাওয়ার কনজিউম করতে শুরু করেছে, তার মানে এটা বুঝতে হবে যে ও কিন্তু আন্ডার এক্সাইটেড কন্ডিশনে রান করছে। আন্ডার এক্সাইটেড কন্ডিশন তখনই হবে যখন ইএফটা তোমার বেশি জেনারেট করতে পারছে না, ঠিক আছে। কারণ ইএফটা যখনই বেশি হবে, তখনই তোমার জেনারেটরটা কিন্তু ইট উইল বি গিভিং ওয়ার টু দ্য সিস্টেম। It will কিন্তু absorb, it will not absorb power from the system. Understood?
স্যার ইএফ ভিটির থেকে কম হলে আন্ডার এক্সাইটেড বলবো, কিন্তু কন্ডিশনটা তো ইএফ কস ডেল্টা, সেটা
হ্যাঁ
থেকে তো স্যার
কিন্তু,
ডিরেক্টলি ইমপ্লাই করা যায় না যে ইএফটাও কম হবে।
হ্যাঁ কেন ইএফটা কম হবে, কারণ কারণ আমি বলছি, কারণ যে এই যে ডেল্টা ভ্যালুটা আমরা আমরা পাওয়ার অ্যাঙ্গেলে কত দেখলাম, ডেল্টা ইকুয়াল টু 90 ডিগ্রিতে ম্যাক্সিমাম হয়, ঠিক তো।
ম্যাক্সিমাম
কিন্তু ডেল্টা ভ্যালুটা কিন্তু ইন রিয়েল লাইফ দ্য ডেল্টা ভ্যালু ইজ ভেরি
স্যার
ভেরি
কম
লেস,
হয়। হ্যাঁ
ভেরি
হ্যাঁ
ভেরি লেস। ইট ইজ অ্যারাউন্ড 20 to 30 ডিগ্রিজ ম্যাক্সিমাম,
ইয়েস স্যার।
ঠিক আছে। তাহলে তোমার তো ইনহেরেন্টলি ভ্যালুটা কম হবেই তোমার সব সময়। ওকে, আর তুমি যে বলছো যে ইএফ এর, শুধু ইএফ এর রেসপেক্টে, ইএফ তুমি তোমার ইএফটা যদি ভিটির থেকে, তুমি বলছো ইএফটা যদি ভিটির থেকে বেশি হয়, সেইটা বলছো তো। কিন্তু ইএফটা ভিটির থেকে বেশি হতে পারে না, কারণ যদি বেশি ইএফটা ভিটির থেকে বেশি হতো, তাহলে সবসময় জেনারেটর কিন্তু মানে ওয়ারই সাপ্লাই করতো, ও কনজিউম করতো না, ঠিক আছে। ও কিন্তু তোমার রিয়াক্টিভ পাওয়ার সাপ্লাই থেকে নিচ্ছে। প্লিজ try to understand this, that its job is to supply power to the system. এটা যদি জেনারেটর হয়, ও সবসময় পি প্লাস জে কিউ দেওয়ার কথা, ওকে। ও সবসময় ও পি দেবে আর কিউ কনজিউম করবে, সেটা সেই সিচুয়েশনটা কিন্তু বলতে পারি যে রিয়াক্টিভ পাওয়ারের এক্সাইটেশনে there is some issues because it is consuming reactive power. It should always be the opposite, it should be always be giving power to the system, okay. সো এইখান থেকে কিন্তু তাহলে আমরা কি আবার ইনফার করতে পারছি, we can infer again that if the reactive power flow is more, then the voltage drop will be more, okay. If the means if we want to change the reactive power, then we have to go for the voltage control of the power system. So voltage control of the power system can be done by changing the reactive power flow of the particular system. If that is the case, then voltage control of power system is possible by changing the field current of the synchronous generator. Field current change করা মানে IF চেঞ্জ করছি, IF চেঞ্জ করছি মানে আমরা ওটার মানে আমরা we are controlling the voltage, okay. If we control the voltage, then we can actually controlling the our reactive power flow of the system. Understood? ওই জন্য এই যে কন্ডিশনটা বাবা বলছি that P and delta is strong coupled and Q and VI is strong coupled, and we are all will be seeing later that the load frequency control that we are talking about and the AVR that we're talking about AVR is automatic voltage regulator that we're talking about, they can be designed separately because of these two conditions, or rather these four conditions. Okay, আমরা বলতে পারি স্যার ভোল্টেজ চেঞ্জ করলে পাওয়ার তো চেঞ্জ হবেই, yes it will change, but that change will be very weak compared to the other part. Okay, so এই রেসপেক্টে আমরা সিনক্রোনাস মেশিনস যখন আলোচনা করছি, এই রেসপেক্টে আরেকটা মেশিনস আমাদের জানা উচিত, that is our synchronous motors. Okay, synchronous motor is also a very important element of the power system. So as you can see the diagram here, so it is actually drawing power from the system. Okay, it is drawing power from the infinite bus. So what is the phasor diagram? Let us see the phasor diagram of the synchronous motor. Again here constant power, as it is drawing constant power but its excitation is varied. Synchronous motor তাহলে phasor diagram টা just synchronous generator opposite হবে. So as you can see here that in its overexcited condition the power factor is how much? The power factor is leading for a synchronous motor. So the synchronous motor is supplying positive reactive power to the supply during its overexcited condition, and during its underexcited condition what is happening, that the motor is drawing reactive power from the supply. Okay, it is drawing reactive power from the supply that is under its underexcited condition. So because of this what we can say property, or what we can say that because of this feature of the synchronous motor, an overexcited synchronous motor running at no load is used for our voltage control in our power system. Okay, an overexcited synchronous motor running at no load is used for our voltage control. Why? Because an overexcited synchronous motor is supplying a positive reactive power to the supply. Okay, so what is the name of an overexcited synchronous motor running at no load?
Synchronous condenser.
Synchronous
Correct.
condenser.
It's known as a synchronous condenser. Okay, so an overexcited synchronous motor running at no load and supplying reactive power, that is known as a synchronous condenser, and that is used for a voltage control. So it is a very convenient device to keep the receiving end voltage constant under any load condition. Okay, so when the load is high, what will happen? Load is high মানে load যখন বেশি হয়ে যাবে, suppose একটা বাস আছে, সাপোজ কনসিডারিং এ জেনারেটর এন্ড এন্ড এখানে একটা লোড আছে. ওকে, ইফ লোড ইজ ভেরি হাই হোয়াট উইল হ্যাপেন?
ভোল্টেজটা লো হয়ে যাবে,
ভোল্টেজটা লো হবে এই পার্টিকুলার বাসে. সো এই বাসের সাথে এই কারেক্ট রিসিভিং এন্ড. ওকে, সো এই রিসিভিং এন্ডের যে অন্য কানেক্টেড লোড গুলো L1 যদি ভেরি ভেরি হাই হয়ে যায়, সো অন্য কানেক্টেড লোড গুলো দে উইল অলসো বি ফেসিং আ লো ভোল্টেজ. Correct? So what will happen then? So we have to run the synchronous generator that will be, and since it is running in this way, so that is also known as sometimes our synchronous phase modifiers or bole oderke. Okay, they are also known as our synchronous phase modifiers also. Okay, so these synchronous generators are run synchronous motor is run in overexcited condition. So VAR is supplied to the system so that the voltage of this particular bus bar reaches its nominal value. Similarly, when the load is low, the machine is run at underexcited condition. Okay, similarly when the load is low, the machine is run in underexcited condition because it is drawing reactive power from the supply. এত অবধি কোনো প্রশ্ন?
No sir.
Okay, so we'll be finishing our class with the limits of overexcitation for synchronous generator and limit for underexcitation for a synchronous generator. কেউ বলতে পারবে what is the limit of overexcitation for a synchronous generator? What is the limit of overexcitation? Overexcitation মানে কি? মানে EF টা is greater than the terminal voltage, তাই তো? If that is the case, সেটা কখন হচ্ছে? কখন হচ্ছে? যখন
রোটরের ফ্লাক্স
amount of field current. EF টা বেশি মানে কি? There is more amount of field current in the system, because বললাম না that EF is produced by phi F and phi is proportional to IF. সো IF যদি ইনক্রিজ করে 5টা ইনক্রিজ করবে, and 5 and EF are in কি বললাম যে they are proportional. So if 5 যদি ইনক্রিজ করে EF টা ইনক্রিজ করবে, yes. So
Yes, sir.
overexcitation is due to the increase in the field current, correct? So if the field current increases, আমি কি যা ইচ্ছা field current increase করতে দিতে পারি? The answer is no, because if the field current increases, what losses will increase in the field windings? I square R loss.
Yes, sir.
So what will happen then if I square R losses increase? The rotor
হিট হবে
heats up. The rotor
Heating.
heats up. Okay. So the maximum value of reactive power that can be drawn from the synchronous generator depends upon rotor heating. Okay. It depends upon rotor heating. Okay. ঠিক আছে? So what is the limit of under excitation of synchronous generator? কি হতে পারে? Under excited হলে কি হচ্ছে? Under excitation
স্যার
হলে কি হচ্ছে?
এক্সাইটেশনটা কমানো হচ্ছে।
না, under excitation হলে
ইন্ডাক্টর মতো
the limits of
স্যার
of
আন্ডার
under excited কি
এক্সাইটেড
হবে?
হয়ে গেলে স্যার IF টা কমে যাচ্ছে।
Correct.
IF টা
IF টা কমছে মানে field current টা কমছে। Field current টা কমলেও what is happening to the power factor? It is changing from lagging to leading. And what happens to the delta value? Delta value is delta increases. Okay. কিন্তু আমি delta কতটা maximum আমরা increase করতে পারবো?
90 degree.
90 degree. So as the field current reduces or decreases, power factor goes from lagging to leading, delta increases. So the maximum permissible increase in delta is up to 90 degree for stability reasons. So the stability of the generator determines the limit of under excitation of a synchronous generator. Understood?
Yes, sir.
Any questions till now? Any questions? If there are no questions, then we are stopping the class here. Yes, any questions? Yes or no?
ফিল্ড কারেন্টের সাথে পাওয়ার ফ্যাক্টরটা একবার একটু যদি বুঝিয়ে দেন।
ফিল্ড কারেন্টের সাথে পাওয়ার ফ্যাক্টরটা
স্যার ওই লাস্ট স্লাইডটাই স্যার।
এইটা
স্যার লাস্ট মানে ওই আপনি বললেন না ওই আন্ডার এক্সাইটেশনের ক্রাইটেরিয়াতে
হ্যাঁ,
বললেন না।
এইবার খেয়াল করে দেখো, এই যে ওভার এক্সাইটেড কন্ডিশনে তুমি কি দেখছো? এই যে ডেল্টা ভ্যালু,
ইয়েস স্যার।
এই যে কারেন্ট ভ্যালু, এই যে
Yes, sir.
থিটা, পাওয়ার ফ্যাক্টর ল্যাগিং তো ওভার
Yes,
এক্সাইটেড কন্ডিশনে। আন্ডার এক্সাইটেড কন্ডিশনে কি হচ্ছে? এই যে ইএফ ভ্যালু, ইএফ ভিটি, এটা আই এ, আই এটা কি করছে? ভিটির সাথে লিড করছে না ল্যাগ করছে?
এটা
লিডিং হচ্ছে।
লিড করছে। ইয়েস স্যার।
আর ডেল্টা ভ্যালুটা কি করছে? ইনক্রিজ করছে। আমরা বরঞ্চ এই ছবিটা থেকে আরো ক্লিয়ারলি দেখতে পাচ্ছি, কারেন্টটা যখন কমছে ডেল্টা ভ্যালুটা ইনক্রিজ করছে, তো ডেল্টা 3 ইজ গ্রেটার দেন আওয়ার ডেল্টা 2।
ইয়েস স্যার।
খেয়াল করে দেখো, ডেল্টা 2 হচ্ছে দিস EF2 is basically the over excited condition, and this EF3 is basically the under excited condition. So delta 3 is greater than delta 2.
ইয়েস স্যার।
So as the field current is reducing, the power factor is going from lagging to leading, and the delta value is also increasing. So if the delta value is increasing, so maximum decrease in field current, maximum permissible decrease in field current কত হতে পারে? যথা delta equal to 90 degree অবধি যেতে পারে, corresponds to delta equal to 90 degree, correct?
Yes, sir.
Okay, so delta equal to 90 degree আমরা cross করতে পারবো না because of the stability issue here, because this region is the unstable region, correct?
Yes,
So
sir, yes.
the stability of the generator determines the limit of under excitation. মজার ব্যাপার হলো এইটা যেটা আমরা দেখছি, এটা হচ্ছে এই কন্ডিশনটাকে বলা হচ্ছে অ্যাকচুয়ালি উইথ রেসপেক্ট টু দিস পাওয়ার অ্যাঙ্গেল কার্ভ, এই যে আমরা বলছি স্টেবল এন্ড আনস্টেবল, এই কন্ডিশনটাকে বলা হচ্ছে কিনা দিস ইজ স্পেসিফিক্যালি ফর আওয়ার স্টেডি স্টেট স্টেবিলিটি স্টাডিজ। ওকে, যখন আমরা ট্রানজিয়েন্ট স্টেবিলিটি দেখবো তখন কিন্তু আমরা দেখবো দ্য ডেল্টা ভ্যালু ক্যান অ্যাকচুয়ালি means it can go beyond delta equal to 90 degree, but that is a different issue. We will be talking about it again in our stability classes. সেখানে দেখবো ট্রানজিয়েন্ট স্টেবিলিটিতে কি ডেল্টা কিন্তু 90 ডিগ্রি ক্রস করতে পারে। ওকে, কিন্তু একটা কিছু সিস্টেম থাকবে নিশ্চয়ই যাতে সিস্টেমটা টোটাল পাওয়ার সিস্টেমটা যাতে স্টেবল কন্ডিশনে থাকে। পাওয়ার সিস্টেম যদি স্টেবিলিটি লুজ করে কি হয় আমরা দেখেছি, উই হ্যাভ ফেস দ্য সিচুয়েশন, ব্ল্যাকআউট মনে আছে 2012 না 13 সালে?
Yes, sir.
দুদিন ধরে। So we can very well imagine that if a loss of synchronism occurs, what kind of condition can it lead to? Okay, so
that was a very good example rather for power engineers to study what a loss of synchronism can actually do. Okay, আচ্ছা আজকে যা যা পড়ালাম তোমরা এলগার্ডের বইয়ে পেয়ে যাবে। ওকে, ইলেকট্রিক এনার্জি সিস্টেমস থিওরি ইবুক মোস্ট প্রবাবলি মনে অ্যাভেলেবেল আছে, তোমরা এটা খুঁজে নেবে, নাহলে তো বইটা তোমরা কিনে ফেলতে পারো। বিকজ ইফ ইউ ওয়ান্ট টু স্টে ইন দিস পাওয়ার সিস্টেম ডোমেন, স্পেসিফিক্যালি ইন দিস কোড ডোমেন, দেন দ্যাট বুক উইল বি অফ ইমেন্স হেল্প টু ইউ। ওকে, আমি আগে আবার রিপিট করছি, দ্য বুক নেম ইজ এলগার্ড, মিনস দ্য রাইটার নেম ইজ এলগার্ড ইলেকট্রিক এনার্জি সিস্টেমস থিওরি। Okay, you can find that book. Whatever I have taught today in and the previous class, I have taken from this portion only, from this book only. For reference, you can take another book, but that will be a very important book, but rather more detailed. অত ডিটেলস এখন লাগবে না, মাস্টার্সে লাগতে পারে বা তোমরা যখন ইলেকটিভ নেবে পাওয়ার সিস্টেমে সেটাতে লাগতে পারে। The book name is Power System Stability and Control by P. Kundur. Okay, Power System Stability and Control by P. Kundur. Very good book, very old book, but still is being used because the quality of the book is very good. Okay, you can use that book also for your reference. You can use these two books, specifically এলগার্ডটা পড়লে ক্লাস করলে আর অসুবিধা হবার দরকার নেই। তবু যদি বুঝতে না পারো তোমরা নাগরাত কোঠারি তোমরা দেখতে পারো। ওকে, ইউ ক্যান ইউজ নাগরাত কোঠারি অলসো। ডব্লিউ.ডি. স্টিভেনসনের বইটাও আছে, স্টিভেনসনের বইয়ে একটু মানে টাফ হবে বুঝতে, কারণ আমার মনে হয় ওটা, যাই তোমাদের নাও হতে পারে, একটু ইংলিশটা অত মানে সোজাভাবে বলা নেই যতটা না তোমার এলগার্ডে দেওয়া আছে। ওকে, আজকের ক্লাসের অবধি। ওকে, সো থ্যাংক ইউ এভরিবডি, থ্যাংক ইউ ফর জয়নিং দ্য ক্লাস। Thank you everybody. Thank you. You may leave the class now.
Thank you, sir.